All right, continuing on in Chapter 4, the next topic is called Newton's method, and this is section 4.8. Now, folks, the derivation of Newton's method is pretty straightforward, but it's going to require us to head off to the chalkboard. So at this time, folks, I'm going to head to the chalkboard and we're going to derive exactly what Newton's method is. All right, we're going to develop what Newton's method is all about. So I have the graph of some function here. Don't know what the function is, don't care. I've labeled this as C. So from algebra, we would have called C, we would have said it's a zero of the function. It's an x-intercept of the graph. It's a solution to setting the function equal to zero. That's what it means to be a zero. So what we're going to do, what Newton's method does is, how can we approximate the zero of this function? So here's the game. Pick a value of x that's close to the zero and call it something. So I'm going to just pick this value right here and I'm going to call it x sub 1. And I can come up to the function. Okay, that's the point x sub 1, f of x sub 1. And what I could do is I could come up with an equation for the tangent line at the point x sub 1, f of x sub 1. And it would look something like, here's what the tangent line would look like. So we could come up with an equation for that tangent line. So keep in mind, to get an equation for the tangent line, to get an equation for any line, you need to know a point on the line and you need to know the slope. Well, the slope of the tangent line is given by, so the slope of the tangent line is given by f prime evaluated at x sub 1, whatever that x sub 1 is. So our equation of the tangent line that goes through the point x sub 1, f of x sub 1, with slope of f prime of x sub 1, well, if we use the point slope form, we'd have y minus y sub 1, y minus f of x sub 1, equals m times x minus x sub 1. Or I could write that in a familiar way. And when I say I could rewrite it in a familiar way, remember that's our linear approximation. But here's the deal. Do you notice that the x-intercept of this tangent line, so there's the x-intercept of the tangent line, doesn't it look like the x-intercept of the tangent line is even closer? Doesn't it look like it's closer to the actual zero of the function than where we started? Well, of course it is. So let's find the x-intercept of this tangent line. Now remember, to find the x-intercept, you let y equal 0. So you let y equal 0, so you get 0 equals f of x sub 1 plus f prime of x sub 1 times x minus x sub 1. So we're trying to solve for x here. So in trying to solve for x, I would subtract this from both sides of the equation, and then divide both sides of the equation by f prime of x sub 1. So that gives me this. And then I add x sub 1 to both sides. Now I'm just going to rename it. I'm just going to rename this x because, my first guess was x sub 1. So this x-intercept, which would be even closer, I would just simply rename that x sub 2. So this is x sub 2. And x sub 2 is a better approximation to the 0. Repeat the process. Come down to the curve. The coordinates of that point right there are x sub 2, f of x sub 2. Get the equation of the tangent line. That's the point of tangency. So here's what the graph of the tangent line would look like. Doesn't it look like the x-intercept of the yellow tangent line is even closer to the actual 0 than what x sub 2 was? Of course it does, because it definitely was. So if we go through the process of getting the equation of that tangent line, which I would say that would be a good activity for you to do. I'm not going to go through this process again, but you could. You need to get the slope of the tangent line. Well, the slope of the tangent line would be f prime of x sub 2. You would use point slope form, solve for x, and I would rename that x-intercept x sub 3, and you would find that x sub 3 is equal to x sub 2 minus f of x sub 2 over f prime of x sub 2. Then you repeat the process. So, you would come up here, boom, there's that point on the graph of the function, x sub 3, f of x sub 3. You would get a tangent line, get the equation of the tangent line, and I think that x-intercept of the tangent line is even closer to the actual root. And if you go through this whole process again, you would rename that tangent line's x-intercept x sub 4, and you would get x sub 4 equals x sub 3 minus the f of x sub 3 all over f prime of x sub 3. Then you would repeat the process, etc., etc., etc. So I'm going to write down the most in general form. Hopefully you're seeing a pattern here. Hopefully you're seeing that this subscript is one more than these subscripts. So x sub n plus 1 is equal to x sub n minus the f of x sub n over f prime of x sub n. And folks, it is this piece here. That's the piece that is like the guts of what is called Newton's method. So what we're going to do is we're going to head back to the slides, and I want you to, as we head back to the slides, and I'll mention this when we get back to the slides, because we went through the process, and then we would just keep repeating the same process, to get x sub 3, x sub 4, x sub 5, etc. We just keep repeating the exact same process. This is ideally suited for us to write a program for your calculator and call the program, Newton. It's ideally suited for that, and we're going to head back to the slides, and we're going to discuss doing just that task, writing a program for your calculator to do this. So let's head back to the slides and see what the program looks like.
All right, as we saw, in the process of Newton's method, it's kind of a recursive creation, and because of that, it's ideally suited for a calculator program. On the course Blackboard site, you will find a handout containing a calculator program for Newton's method, and you should, get this written into your calculator. Get this program in there. I mean, here's what it is. This is the program itself. And in fact, I'm gonna call up my calculator, and I'm gonna write the program right now. So let me pull the calculator over here. So when I write a program, I click on the program button. I'm making a new program, so I hit enter. Okay, the name, I'm calling it Newton. So N-E, there's W-T-O-N. All right, so now enter. So the first line of the program is prompt X. Now prompt is a programming command. It's hidden under PRGM, and it's either a CTL or an IO. I don't see it in this list, so I'm just going to go over to IO. Oh, there it is. So number 2, prompt X, new line. Okay, LBL, that's another programming command. Oh, there it is, number 9. So LBL-A, so I have to do alpha first, A, new line. Okay, X minus, this line is the actual line of Newton's method. So it's X minus Y sub 1 of X. So I have to find Y sub 1. Okay, Y sub 1 is hidden under vars. I go over to Y vars, function, and there it is. So Y1 of X divided by, okay, Y sub 2, that's hidden under vars. Function, and it's 2, okay, of X. And that is the arrow, that's the arrow button. That's sent to X. Enter. Okay, now display X. We wanted to display each approximation to the root. That's why we have to say display. So, oh, there's display. It's under IO. So 3, then X. Hit enter. Okay, pause. If I don't put pause in here, the program's going to run so fast I can't. I won't be able to read anything. Oh, so program. Pause is number 8. Enter. Okay, now go to, that's hidden under program. I believe it's down here. I believe it's 0. Let's look and see. Yep. So go to alpha A. All right, so that's the program. So we have the program entered, into our calculator, or I have it entered into my calculator. I think we're ready to look at an example. I'll have to call my calculator up here in a minute. So we're going to consider the function f of x equals 3x squared minus 2. Part A, use the intermediate value theorem to show f has a 0 and 0, 1. Well, I'm going to do that real quick before, I'm just going to talk about it before we do part B. The intermediate value theorem, we know the function is continuous on the closed interval 0, 1 because the function is a polynomial function. F of 0 is -2. F of 1 is 1. So 0 is between -2 and 1. So, yep, the function has a 0 on the closed interval 0, 1. Part B, we're going to run the Newton's method program to find the 0 in the interval 0, 1. Okay, here's how you're going to write stuff down. I'm very adamant about this. You're going to write down what your initial guess is, and then each successive approximation that's generated by Newton's method. You will stop when 2 consecutive approximations agree to all decimal places. So let me call up my calculator again, and here it is. So okay, here's what you have to remember. You have to put into y1 the function. So the function is 3x squared minus 2. And then in y sub 2, you put the derivative of the function. Well, the derivative of the function is 6x. Okay, now to use Newton's method, to use the program, you have to have an initial guess. That's what that one line that says prompt X is. It's going to ask you for an initial guess. So here's how you would get an initial guess. Look at the graph of 3x squared minus 2 and kind of see where it crosses the x-axis in the interval 0 to 1. I've already done that. My initial guess is going to be 0.8. So I would write down 0.8. Now I'm going to run the program. So let me quit out of here. Program, Newton. So I'm going to execute the Newton's method program. So I hit enter. Then I hit enter to really run it. Here's my initial guess, 0.8. So I write that down. Okay, that's one time through Newton's method. That's the next approximation to the actual 0 that's in the interval 0, 1. So I would write that down, all the decimal places. Now I hit enter because right now the calculator, it's stuck on the line that says pause. And that's so we could write this down. So I hit enter. I write this number down. I hit enter. I write that number down. I hit enter. I write that number down, and now I'm done. I have 2 consecutive numbers on the calculator that agree to all decimal places. And no matter how many more times I go through Newton's method, each time I hit enter, I'm doing another trip through Newton's method. That number will not change. So you see this on a test, you need to write down what your initial guess is, and then you write down each of these numbers until you see 2 that agree to all decimal places. Now, the structure of Newton's method program, I have it set up as like an infinite loop. So to break the infinite loop, you come down here and you click the on button. Okay, there it broke. So I hit on to stop the program, and it gives you an error, but that's okay. Just hit enter, and now you've quit the program. And when you quit the program, now the calculator, you could do normal stuff. You could do 2 times 3 to get 6. All right, so let's look at what is next. I believe I'm going to have an example that I want you to do. So you're looking at the function cosine x minus x. I'm saying it does have a 0 in the interval 0 to 1. Run your Newton's method program to find that 0 in the interval 0 to 1. So just as I've said, list your initial guess and each successive approximation that's generated by the Newton's method program. Stop when you have 2 consecutive approximations that agree to all decimal places. So again, remember, you have to put the function in y1. You have to put the derivative of the function in y sub 2. You should probably look at the graph of the function cosine x minus x to kind of give you an idea what your initial guess is going to be. So go ahead, pause the video. Do this example. When you're done, restart the video. I'll be here with my calculator, and we'll be going through Newton's method. All right, let's see how you did here. So let's see, I have to get the function cosine x minus x, and it's y sub 1. And then y sub 2, the derivative of the function. So that's negative sine x minus 1. Let me quit that. Let me quickly make sure I'm in radian mode. Okay, I am. Now I'm going to execute my Newton's method program. When I graphed cosine x minus x, I decided I was going to do an initial guess of 0.7. Okay, so that's my first trip through Newton's method. There's my second trip. I'm going to write these numbers down on my paper. There's the third trip, fourth trip. It looks like I've now hit 2 consecutive numbers that agree to all decimal places. So I am done. I'm done with Newton's method. And then remember, I hit on to stop the program, to break the program. So that's all there is to this section. It's a short, sweet, I think pretty friendly section. So at this time, you could do the exercises that I've listed for you to do in section 4.8. So go do the exercises. Have fun with the program. Thanks for watching.